Welcome to the third lecture of my series on tensors under general coordinate transformations. First, the customary recap. As we have seen over the last couple of lectures, under a coordinate transformation x going over to x prime, which is some in general non-linear function of x, vectors which are written with superscripts transform in exactly the same way as coordinate differentials do. A prime mu is del x prime mu del x nu a nu, and of course the summation over nu is implied here, and these coefficients, derivatives of the new coordinates in terms of the old ones, are what we call vector transformation coefficients. Covectors, on the other hand, transform in an opposite manner. There you again have a linear combination of the old components, but now the coefficients are partial derivatives of the old coordinates with respect to the new ones. Now, if you have a mixed tensor of higher rank, its transformation will have as many vector transformation coefficients as there are upstairs indices and as many covector transformation coefficients as there are downstairs indices. So it is pretty straightforward to write down the transformation rule for any tensor just by following this basic rule. Now, the important result that we derived in the last lecture started with this negative result that the partial derivative of a covector field is not a tensor under general coordinate transformations. If you carry out a transformation x going over to x prime, you end up with del mu a nu going over to del mu a nu prime, the value in the new coordinates, which is given by del x a del x prime mu del x b del x prime nu del a a b, plus another term del 2 x a del x prime mu del x prime nu capital A a. Note that if these were linear transformations, then del x a del x prime mu would be a constant and its second derivative would then vanish. So this extra term, which is what is ruining the tensor nature of del mu a nu, would have been absent for linear transformations. When you carry out nonlinear transformations, you no longer get tensorial behavior, which you would get for linear transformations, for the simple reason that although this term behaves exactly as a tensor, a 0, 2 tensor would actually transform as, this extra piece completely ruins that. Now, as we had stated then, differentiating objects among them covector fields is actually very, very important in physics applications. And the fact that such a differentiation does not lead to a tensorial object actually makes our life a bit difficult. However, in order to remedy this situation, we define a special kind of derivative, something called a covariant derivative. Written capital D mu a nu, it is basically del mu a nu, to which a correction term minus gamma lambda mu nu a lambda has been added. And what you demand is d mu a nu under transformation of coordinates must become del x a del x prime mu del x b del x prime nu dA ab exactly the way a 0-2 tensor is supposed to behave. Now, in order to ensure that, what you must demand is that these dq functions, gamma, lambda, mu, nu, must transform under general coordinate transformations in the following manner. Well, actually I have written down the transformation for gamma prime mu nu lambda rather than lambda mu nu, but that should not really be a problem. Notice that in this transformation rule, you have a piece which is exactly like the transformation for a 1, 2 tensor, something which these indices, one upstairs and two downstairs indices, seem to suggest for gamma, that is del x prime mu del x a, del x b del x prime nu, del x c del x prime lambda, gamma ABC. However, in addition to this, you actually have one more term, which is basically del x prime mu up here, del x prime nu, del x prime lambda in the second derivative here, with a single old coordinate xa being the differentiatee and the differentiated, so to speak, and of course this is summed over all A. A is of course a dummy index. Now the important thing is, this inhomogeneous piece that you have in gamma prime mu nu lambda's formula, this piece which is not linearly dependent on the original gammas, and this inhomogeneous piece that you have in the transformation for del mu a nu actually leads to a cancellation, and you end up with d mu a nu, the covariant derivative, actually exactly transforming like a 0-2 tensor. Exactly what we would have loved to have for del mu a nu, but we don't. So we have to introduce this kind of a correction term to end up with a covariant derivative. Now, I have promised that I am going to talk a lot more about the geometrical meaning of these correction terms, the so-called connection and so on. That we will do in the later half of today's lecture. But first, let me try to explore the algebraic features of the connection. In particular, let us begin with the question. This is how you transform a derivative of a covector field into a covariant derivative. These are the additional correction pieces you have. How would you carry out the same process for the derivative of a vector field? So, basically what we are asking is, how can we find a covariant derivative d mu a nu where the field being differentiated is a vector field? Before we can answer that, we have to put in two very basic things in place. The first of them is, how would you carry out a covariant derivative of a scalar field? Now, for a scalar field, which is of course a rank 0 tensor, the ordinary derivative del mu phi already leads to a one form, the gradient. That is, it already leads to a 0,1 tensor. So, in order to make this into a covariant, that is a tensorial object, you do not have to look any further. There are no additional correction terms necessary here. So, what we would do is we would take the simplest possibility. The covariant derivative of a scalar field will be defined essentially to be the same as the ordinary partial derivative. And what we would then demand is that the Leibniz rule works. Remember, the Leibniz rule for ordinary derivatives is simply nothing but this rule. Del x of a product uv is del u del x times v plus u times del v del x. And this is something which we want to generalize for any kind of product of tensorial objects when the covariant derivative is involved. So what we would want is d mu acting on a product. This could be an outer product, could be an inner product, and these dots are just indicative. I do not really imply that A and B are 2,2 tensors each. We could have had, say, more dots or less dots. The dots, of course, indicating indices. The basic point is, when you take this outer product or maybe even a contraction with an outer product in place, that is some lower rank tensor than just the number of dots is suggesting here, to carry out its covariant derivative, whatever process you adopt must give you this result, that this covariant derivative of the product is basically A times the covariant derivative of B plus covariant derivative of A times B, exactly the way the ordinary products are differentiated in elementary calculus. Now, armed with these two basic results, we will now try to figure out what is the covariant derivative of a vector field. Well, we start with the fact that A upper nu, B lower nu, where A is of course a vector field and B is a covector field, gives you a scalar. So, according to our first basic principle, the covariant derivative for this product must be the same as its partial derivative. Now, the Leibniz rule that we demanded for the covariant derivative would immediately tell us that you will have covariant derivative of A nu times B nu plus A nu times the covariant derivative of B nu on the left hand side. On the right hand side, you can immediately use Leibniz rule because this is nothing but ordinary derivatives, and there we know that the Leibniz rule works. Strictly speaking, this is not just a product that you have a sum of a product, but you can easily figure out that the Leibniz rule works for that as well. So now, what does this tell us about d mu A nu? Well, d mu A nu can be figured out from this. This term, d mu A nu B nu, is simply nothing but the sum of these two terms minus this. And when I move this to the other side, I have actually written this out. That is, d mu B nu, the covariant derivative of a covector field, is something we already have a formula for. So, minus A nu times del mu B nu, the ordinate derivative, minus gamma lambda mu nu B lambda. This, remember, is exactly how d mu B nu for a covector field is defined. Now, you can easily see that this term cancels out this term. So, what we have is covariant derivative d mu of a vector field component A nu contracted with B nu is the same as del mu A nu B nu plus A nu gamma lambda mu nu B lambda. Now, we would be able to deduce from this that whatever is sitting in front of B nu has to be the same on both sides, simply because this has to be valid for all covectors B. The only hurdle to that is, although we have a B nu on this side, in this term we have a B lambda, but that's easily remedied. Note that this lambda is a dummy index, so of course is a nu. So all we would do to get a B nu here is switch the names for nu and lambda. So I'm going to call this pair lambda and this pair nu. So that makes this expression become del mu A nu B nu, that's just this term, plus this with the switches A lambda gamma nu mu lambda B nu. So d mu A nu, the thing that we want to find out, contracted with B nu for arbitrary B nu is the same as del mu A nu plus A lambda gamma nu mu lambda contracted with B nu. And as we have already said, the B's can be completely arbitrary, so the coefficients must match. Therefore, the formula for the covariant derivative of a vector field simply works out to be d mu A nu, A upper nu is del mu A nu plus gamma nu mu lambda A lambda. Note that apart from the fact that this is a plus sign here as opposed to the covector field derivative case where you had a minus sign. The other difference is simply one which you could sort of get the hang of by simply looking at the placement of the free indices. So the mu is downstairs here, it of course goes downstairs. The upstairs mu goes upstairs in the gamma. The other index is just a dummy index, has to be downstairs on gamma and upstairs on A. So just to remind you once again, the mu A nu would be del mu A nu, the ordinary derivative, minus gamma. Now let's look at the positioning of the indices. Mu nu's are both downstairs, they go on the downstairs part of gamma. The upstairs index is a dummy index which has to be contracted with A's index. So you could write that as lambda or rho or sigma or anything you want. So apart from the fact that a covector field's covariant derivative has a minus sign and a vector field's covariant derivative has a plus sign, the rest can be sort of figured out just by looking at a proper positioning for the indices. Now that we have derived using the demand that Leibniz rule works, a formula for the covariant derivative of a vector field, we can turn back and ask the question, is this result really a tensor? Of course, given the positioning of the indices, this could be a 1, 1 tensor, a mixed tensor. But is it? Let us just give you a proof that it is. In fact, I will do better than that. I will give you two distinct proofs that this d mu a nu that we have derived here is actually a 1, 1 tensor. Let me give you the first answer, the easy one. The easy one actually hinges just on the Leibniz rule. Note that we derived the expression for d mu a nu by invoking the Leibniz rule here. Now let us examine the terms on the two sides carefully. This whole thing, the entire right hand side here, is nothing but the partial derivative del mu of a nu b nu. This is a scalar. And its partial derivative, this whole side has to be a 0, 1 tensor, a covector field. Now what about this? This is a 1, 0 tensor, and this d mu b nu we already know has to be a 0, 2 tensor. In fact, the whole thing about connections and the transformation rules etc. was to ensure that this turns out to be a 0, 2 tensor. And here of course you have a contraction on the nu. So that automatically makes this thing also, the whole thing, a 0, 1 tensor. Essentially the upstairs index and the downstairs index contributes opposite transformation rules which cancel each other out. Something we had seen in some detail in the last lecture. So on the right hand side you have a 0, 1 tensor, actually a tensor field to be more precise. On the left hand side this piece is a 0, 1 tensor field, and if I bring this to the other side and subtract, it turns out that this whole thing is a 0, 1 tensor field, because it's nothing but the difference between two 0, 1 tensor fields. And now let us look at this object which we want to be a 1, 1 tensor, but we don't know clearly whether it is. But what is definitely true is that this is a 0, 1 tensor, and contracting with this gives you a 0, 1 tensor field. Therefore, this one has to have a 1, 1 tensorial behavior by the quotient law. Note that if you had this and this essentially cancel out and you are going to end up with 0, 1. Or in other words, this upstairs index and this downstairs index ends up contributing opposite transformations, both being tensorial, and therefore you are going to end up with only one downstairs index. Of course, the quotient rule guarantees that d mu a nu has to be a 1,1 tensor. Otherwise, you would not get a 0,1 tensor field on contraction with B lower nu. So this is the more elementary and actually rather simple proof that the derivation that we have done for d mu nu does lead to an actual 1,1 tensor. What we will do next is essentially forget whatever we have said right now and carry out an entirely different independent derivation where we directly use whatever we know about the transformation rules for the quantities on the right hand side and try to show that that is going to end up giving you the fact that d mu nu transforms under a coordinate transformation like a 1,1 tensor should. This proof proceeds as follows. Del mu nu's version in the new coordinate system will simply be del x prime mu a prime nu plus gamma prime nu mu lambda a prime lambda. Note that we know every term on the right hand side and that's what we are going to use now. A prime nu of course is del x prime nu del x b ab, and since this whole thing is a function of the old coordinates x, what we need to do is change this del x prime mu to reflect derivatives with respect to the old coordinates. This of course is nothing but the chain rule for partial derivatives in action here. So this is nothing but the first term. What about the second term? Now in the second term I put in the transformed version for gamma prime nu mu lambda, which essentially will have a piece which is like the tensor, like a 1,2 tensor. So del x prime nu del x a, then this will give you a del x b del x prime mu, this lower index lambda will give you a del x c del x prime lambda, gamma abc. But in addition to that, you have a del x prime mu del x a del 2 x a del x prime mu del x prime lambda as the additional inhomogeneous term in gamma's transformation. You have to multiply that of course by a prime lambda, which is del x prime lambda del x t ad. Now notice that when you carry out this differentiation, you get two terms. One is the term in which del x prime nu del x b is pulled out of the differentiation. This of course is nothing but Leibniz rule. So del x a del x prime mu del x prime nu del x b del a ab. But in addition to that, you have one more term, which is essentially what prevents del a ab from directly being a 1,1 tensor. This additional term is the term that you get when you differentiate del x prime del x nu del x b with respect to with respect to x a. So del x a del x prime mu, that's the factor that you already had, times the second derivative times ab. That's the inhomogeneous term in which ruins the tensor nature of the derivative of a vector field. Now, let's look at the other two terms in a bit more detail. Now, if you look at this term carefully, you will see that del x c del x prime lambda is actually coupled with del x prime lambda del x d. It's contracted here, the lambda index, and therefore, what you can actually easily show that this is nothing but del x c del x d, the product of these two terms, summed up over lambda. And so, you can simply replace these two factors by delta cd. The rest of course stays as it is, del x prime mu del x a, del x b del x prime mu, and gamma abc ad. And finally, this inhomogeneous term for the transformation of the connection, del x prime nu del x a times del 2 x a del x prime mu del x prime lambda, del x prime lambda del x t ad. Now notice that this term is the same as del x prime lambda of del x a del x prime mu, and that has been contracted with del x prime lambda del x d. So this really is del x d of del x a del x prime mu. Now that's what we are going to make use of soon. But first, let us collect the terms together which gives us the right tensorial behavior. This one, of course, is exactly the way a 1, 1 tensor should transform. Of course, you have an additional piece which ruins the transformation. But still, this alone would have been a good 1, 1 tensorial transformation law. And here, once you replace delta CD AD by AC, you get this additional piece which also has the makings of a 1, 1 transformation law. Of course, you might say that here you have an A and a B here with the prime mu and prime nu respectively, and here you have A and B in the opposite derivatives, but that's easily remedied. You can just rename the B's A and the A's B so that you get the same coefficient in front of both. But in addition to those two pieces, you have this one and this one. The first term is del x a del x prime mu, del to x prime mu del x a del x b, AB, and what I have done here is change this D, the dummy index, to B in the second term so that I can take an AB common out from that piece as well. So you have del x prime mu del x a del to x a del x prime mu del x prime lambda del x prime lambda del x b. But now notice that the first two pieces here, after you have relabeled the A and B, which is what these colors are showing you, these two B's here have become both A's, and these two A's originally have become B's. But now, coupling these two terms together will give you exactly del x a del x prime mu del x prime mu del x b into del A AB plus gamma B AC AC, which is nothing but capital D A, capital AB. But what about the extra terms? There we have to be a bit clever. The first term can be written down as the product of del x a del x prime mu and del x b of del x prime mu del x a, of course. That's the second derivative here. What about this? Here, because of the lambda contraction, this term really is the del x b of del x a del x prime mu. But that actually makes life very easy for us. Notice what you're doing is this factor times the derivative of this one, and here your del x prime mu del x a, this factor, times the derivative of this one. So if you just use the Leibniz rule for ordinary derivatives, this piece becomes del x b of del x a del x prime mu del x prime mu del x a. Of course, AB is sitting outside. That's the whole term in the second line here. This is, of course, what we have already said. You collect the coefficients properly, you get this thing, which is nothing but dA AB. Now comes the final piece. You already have dA AB times the proper covector and vector coefficients, but this thing is actually del x b of this product. Because there is a contraction over A, this product is nothing but del x prime mu, so delta nu mu. And delta nu mu is a constant function, its partial derivative is 0. So you are left with the result that d mu a nu's value in the new coordinate system is del x a del x prime mu del x prime mu del x b times dA AB. Exactly what it should have been for a 1, 1 tensor. Now that we have managed to figure out how to take derivatives, covariant derivatives of vector fields and covector fields, and ensure that the resulting things are tensorial, we can go on and talk about tensor fields and how to differentiate them and still keep tensorial nature intact. So just to illustrate the general principle, we will look at the covariant derivative for a 2-0 tensor T mu nu. And we will start exactly the same way that we started our discussion on the vector field with. We will start with the fact that if you supply T mu nu, a 2-0 tensor, with two 0-1 tensors, that is two covector fields, the resulting contraction is a scalar. So, its lambda covariant derivative is the same as its lambda partial derivative. That's true for scalars. And then we will just make use of Leibniz rule. So, Leibniz rule, of course, is for a product of two tensorial objects or two functions, but its generalization to three or more is trivial. Here, just like in ordinary derivatives, this gives you d lambda acting on T mu nu with a mu b nu outside. Then you have T mu nu and b nu outside with d lambda a mu and so on. This is the third term where d lambda is acting on b nu. And of course, on the right hand side, you have exactly similar expression with partial derivatives instead of a covariant derivative. And this is not a surprise at all. This is just a partial derivative of product of functions, the standard Leibniz rule. Now, once again, all we need to do is isolate this piece and figure out exactly how much this is going to be. And for that, what we need to do is replace each of these covariant derivatives, which we know how to calculate, in terms of the partial derivatives and corrections. So this is T mu nu, B nu, this and this sticking outside, and this is nothing but T lambda A mu, del lambda A mu minus gamma lambda mu and sigma being contracted with the A. Similarly, this is T mu nu A mu del lambda B nu minus gamma sigma lambda nu B sigma. On the other hand, on this side, you are actually carrying out ordinary partial derivatives. And now, notice this term T mu nu del lambda A mu B nu is exactly the same as this term, so you can cancel these two terms. Similarly, the term with del lambda B nu here is the same as the term which comes from this term in the bracket. So, d lambda T mu nu contracted with A mu B nu is nothing but the product of these terms, the two surviving terms, moved to the other side. So, del lambda T mu nu A mu B nu plus gamma sigma lambda mu T mu nu A sigma B nu. Thus, this moved to the other side and an additional term gamma sigma lambda nu here T mu nu A mu B sigma. Now, what we need to do is compare the coefficients of A mu B nu on the two sides. After all, A's and B's are arbitrary covectors, so their coefficients should match on both sides. But what we need to do is ensure that you have A mu B nu on both sides. This one is already there, but here you do not have mu for A, you have sigma. But that's handled easily. This and this are dummy indices, so are these mu's. So all you have to do is call these sigmas mu's and these mu's sigma. Similarly, you wanted A mu B nu here, but you have a B sigma. So these two dummy indices sigmas have to be replaced, if they switched with the dummy index nu to achieve an A mu B nu here. So once you do that, this is what's going to happen. The dummy indices which have been switched have been written in black here, so that you can follow exactly what has happened. This sigma in this term has become mu and mu, and these mu's and mu's have become sigma and sigma. Similarly for this. Now that we have two expressions on which you have coefficients of A mu B nu on both sides, we can just compare the coefficients and say that the covariant derivative d lambda of T mu nu must be the partial derivative plus two terms. Now, first of all, you have plus because you have an upstairs index. Remember, covector fields had a minus in the covariant derivative. Vector fields had a plus. This continues into tensor fields as well. upper indices correspond to plus signs. And of course, lower indices would correspond to minus signs. What about the indices themselves? Here, the result is actually quite easy to remember. There are two upper indices on this side, mu and nu, and each of them in turn get to be the upper index of gamma. What about the other piece? The lambda, the covariant derivative that you're carrying out, has to be there as a first index of the gamma below. The other index will serve as a dummy, and essentially sigma and sigma are contracted. If mu is sitting here, the first index of t has to be contracted. If mu is sitting here, the second index of t on this side, then the second index of t here has to be contracted. Now, I can essentially use this kind of rules to write down formulas for covariant derivatives of all kinds of tensors. For example, d lambda of t mu nu, where mu nu is a 1-1 tensor, simply has a partial derivative. Then you have plus sign corresponding to the index upstairs. Of course, that index goes up here. And lambda nu go down. The lambda goes to gamma, the nu goes to t, the lower index of t, and the other index is contracted. What about the lower index nu here? That's going to give you a minus sign. And now, the lambda is the first index of gamma. Nu is sitting down here, as it should. It's also down on this side. The sigma is the contracted one. And t will have an upstairs mu, which has not been touched in this part of the expression. And where you had nu before, that's where you have to get the contraction done. On the other hand, d lambda t mu nu will be del lambda t mu nu for 0 to tensors, both minus signs, and basically the lambda has to be the first index on the gamma both times. Mu and nu essentially will feature in the gamma, but when mu features in the gamma, what was in the place of mu in t, that gets contracted. When nu features into the gamma, the second index, which is where nu was, that gets contracted. I will leave it as an exercise for you to prove that the right hand side of this expression really behaves tensorially. In fact, it behaves tensorially exactly in the manner in which these indices would suggest. That is, this one should be a 2-1 tensor. Similarly, this one should be a 1-2 tensor. It has one vector index, two covector indices, and this one should be a 0-3 tensor. Now, proving that this is true, starting from the right hand side of these expressions and figuring out how the right hand side transforms, is slightly lengthy, but at least doing it once in detail will give you a lot of confidence in handling calculations of similar kind. So this is a useful exercise for you to do. Let me now turn to a different topic, which we have alluded to earlier. Why do we at all need a connection? That is, in order to change a derivative from a non-tensorial object to a tensorial object, why would we at all need to introduce an additional correction term? And the answer to that is something I've already given you before. You cannot directly compare vectors at different points. Vectors at different points belong to two entirely different vector spaces, and subtraction between them or addition is not defined. And one of the first things you need to do when you differentiate a vector field with respect to space would be compare vectors at two different points, which is simply something that cannot be done directly. So, for two neighboring points, let's say P with coordinates x and Q with coordinates x plus dx, the ith component of the vector v at the point P and the point Q respectively, if we were to subtract them, we of course get the kth partial derivative of vi times delta xk, where delta xk is the displacement from P to Q, and of course it's a sum over k. Now this is definitely nothing but the standard rule for total differential of an object. Of course, for finite delta x's, this is really an approximation. There are higher order terms of the order delta x square and above. But for infinitesimally small delta x's, this is essentially the term which contributes. Now, as we have already said, the difference between the ith component of v at q and the ith component of v at p is not the ith component of a vector. vq minus vp is not a vector. And that immediately tells us that this del k vi, this coefficient that is sitting here, despite an upstairs or vector index and a downstairs or covector index, is not a 1-1 tensor. If this had been a 1-1 tensor, then contraction with delta x would have given rise to a 1-0 tensor, that is a vector. So from the fact that you cannot compare vectors at different points, comes the result that the difference is not a vector and therefore the partial derivatives is not a tensor. We have already seen that before, and this is exactly encapsulated in the fact that the way in which del k vi transforms is not the way in which a genuine vector component would transform. So before you can at all do a derivative, which is compare vectors at two neighboring points with each other, so this is the vp and this is the vq, what you need is a way of pushing the vector. Sorry, this is of course a mistake. This is v at q and this is v at p. Before I can compare or the difference between vp and vq, what we have to do is figure out a way of pushing a vector here at P to form a vector at Q. So this is a vector at Q, but that's not the original VQ. It's what is called a parallel transport of this VP. You move the vector VP in some sense without changing it, or at least at best you can do without changing it, from one place to another, keeping the vectors parallel. Now I am putting parallel within quotes because exactly what parallel means is not very clear at this stage. As it turns out, there are many different ways in which you can define parallel transport. We will use standard geometrical notions to establish a particular kind of parallel transport in detail later, but we will see that in action soon. Now, in order to see an example of parallel transport, we will essentially take a cube from flat space. We already know how to do a parallel transport in ordinary daily life flat space. Basically, here we know what parallel means. This blue vector here and this blue vector here are parallel. They have the same length. They have the same direction. Of course, in a general situation, you may not have any notion of length or direction, or the notion of length and direction which you do have may be very alien to what you think length and direction should be like. And we will talk about those things in detail later. But the important point here is that in the standard Euclidean geometry, we have a sense of what parallel transport really means. Same length, same direction in the standard Euclidean sense of the word. Now, notice that Vp, this vector here, I've drawn a two-dimensional vector simply because it's easier to draw, is being transported here to become Vq parallel. Now, does that mean that Vp and Vq, even in flat space, would have the same components? I'm stressing even in flat space because, as you will see later, if the space were not flat, things become way more complicated. But the same mathematics kind of applies. But at least even in flat space where length and direction are preserved, we can still not guarantee that the components will be the same, because the basis vectors that you use at P and the basis vectors that you use at Q may actually be different. And that actually tells you that VQ parallels ith component and VP's ith component will not really necessarily match. They do match if you are using Cartesian coordinates in flat space-time, because the basis vectors are essentially also being parallel transported at the same time. However, here, in general, you will see a change in the components, and the change in any one component, let's pick the ith one, will be bigger if the vector is of course larger. And the change will usually involve all the components of the vector in a linear fashion. It will also depend on all components of the displacement which took you from P to Q. Based on this, what we can say is the following. If you subtract the ith component of Vp from the ith component of the VQ parallel, which remember is Vp's transported version, what you get is the following. You get something which depends on Vp's jth component, delta x is kth component, which are multiplied together here, with coefficients. And what should the coefficients depend upon? The coefficients should of course depend on the point where you are evaluating this, where you are starting from, that is the point P. But other than that, we should have indices which tell you about which particular components are being addressed here. There should be an I index because you are talking about the ith component. So that's the I index here. In addition to that, you are actually adding up contributions for the jth component of V and the kth component of displacement. And the way we define this is we write minus gamma I kj at P. The minus sign here is simply because you want to make it compatible with other usages that we have before. So the gamma symbol, the connection symbol that we had introduced earlier in an attempt to ensure that ordinary derivatives change into covariant derivatives, things which transform like a tensor, these play a role here which is way more direct and geometrical. They simply say how do components of a vector transported parallelly change. And this is essentially going to be my model for all kinds of space. In flat space, this change only occurs because of change in the basis. In curved space, there could be other reasons for the components to change in general geometries. Now, if you want to find the tensorial derivative, that is, of a vector field, the first thing that you should do is end up subtracting vectors at the same point. So instead of VQI minus VPI, the ith component of VQ and VP, what you must do is subtract from VQI the ith component of the vector which is a parallel transported version of VP that has been brought to Q. So you are essentially subtracting two vectors at the same point. Now this is a genuine vector, and we are going to write this result in the same manner as before. Instead of del k vi delta xk, we are going to write this as capital dk vi delta xk. Of course, the way we write this makes it obvious that this thing, the dk vi, is not only a two-index object with one upstairs and one downstairs index. It must actually transform like a 1-1 tensor, because only if it did that, a contraction with delta x will actually lead to a 1-0 tensor, that is a vector. Now, let us make use of our result or definition of these gammas, really, from the parallel transport concept. So what we do is replace VQ parallel I by VPI minus gamma I kj Vj, sorry, this is a type mistake, it should be Vj delta xj. Note, by convention, standard convention, second index here is associated with the vector component in the first index, the displacement. Now, it's easy to see that this is what it ends up being, just opening up the bracket. However, VIQ minus VIP is a change in the ith component of the vector V when you move from P to Q, and that's nothing but del K VI delta XK, something we have already seen before. And collecting this term along with this one gives you del K VI plus gamma IKJ AJ. Sorry, all these are not AJs, these are all VJs. So, into delta XK. So finally, this tells us what delta KVI is. It seems that I have made the same mistake over and over again. dkVi, the covariant derivative, the component of the 1, 1 tensor, is given by del kVi plus gamma ikj vj. Which of course is something which we are already familiar with. This is the way in which you covariantly differentiate a vector field. But here you see the geometrical meaning behind this operation. You are actually not subtracting vectors at two different points. You are pushing a vector from the first point parallel to itself to the second point and then subtracting two vectors at the same point. Now, using this, let's look at an example. And we will see how to calculate these connection coefficients gamma I, kj for a familiar geometry. Now first, what is the geometry? The geometry is a simple standard one of flat space. So, a parallel transported vector in flat space, the standard geometry that we know, changes neither in length nor in direction. So that's what parallel transport means to us, usually in at least ordinary geometry. The vector maintains its direction, maintains its length, only its point of application shifts. Now, this should be a very simple example, and in fact it is. To keep life simple, we are going to keep on working in 2D, but going to higher dimensions is not really going to be a big deal. But in 2D, let's begin with the simplest possible situation. Let's say we are using Cartesian coordinates. Now, remember the basis vectors in Cartesian coordinates at a given point essentially talk about increase in x and increase in y respectively, and essentially they are nothing but I and j. As we have already said, you may be using unfamiliar notation del x and del y for them, but they essentially mean the same as what we used to call I and j. But the I and j at two different points are essentially the same, they are parallel transported versions of each other. What that means is simply this: the components of a vector do not change when you parallel transport it if you are using Cartesian coordinates in flat space. And that of course means that all the connection coefficients, if you are using Cartesian coordinates, must vanish. So, the connection in flat Euclidean geometry using Cartesian coordinates simply is made out of zero functions. All components of the connection, all of them are zero. Now let me point out that I have been stressing the word using Cartesian coordinates over and over again. Remember, gamma I, j, k's are not tensorial. If they had been tensorial, if there had been components of a 1, 2 tensor, then if all the components vanished in one frame, they would definitely all vanish in another frame. That is not really true for gamma I, j, k. Even if the geometry stays the same, the components may be all zero in Cartesian coordinates, but in other coordinates they are not guaranteed to all vanish. In fact, we will soon see that they do not all vanish by going over to a different coordinates. The different coordinate system that we are going to use is not going to be a very esoteric one, it's simply going to be polar coordinates. So let us first try to calculate connection coefficients in polar coordinates. We are going to do that in two different ways. One is basically analytical, you just calculate things, and the other is geometrical. Let's deal with the analytical part first, and that essentially follows from the fact that under a coordinate transformation, x, which of course means x1, x2, x3 up to xd, going to x prime, which are smooth differentiable functions of x, the connection coefficient in the new frame gamma prime ijk transforms in this manner. This piece is essentially the same kind of piece you would expect for a 1, 2 tensor, but in addition to this piece, which is a linear combination of the old components, you have an inhomogeneous term, a term which actually does not depend on the gammas at all, but only on the transformation del x prime I del xa times del 2 xa del x prime j del x prime k. Now notice, in Cartesian coordinates, which are our original coordinates, the ones without primes, and if you are using flat geometry, gamma ABC vanishes. So this first term drops out. So not only in polar coordinates, in any coordinates, as long as the geometry is flat and you have a coordinate system, Cartesian, in which all the gamma ABCs vanish, then in any other frame which is connected to the Cartesian by a transformation law like this, gamma prime ijk is essentially given by this factor, which you can simply calculate from what you know about the transformation function. And I will also attract your attention to one thing. In such a situation, because of the fact that partial derivatives commute, switching j and k will not change the gamma. So at least if you know that there is one coordinate system in which the connection coefficients all vanish, then in all other coordinate systems, the connection coefficients must be symmetric in j and k, the two lower indices. Now this may come as a bit of a surprise to some of you who already have studied differential geometry or general relativity, that I am stressing this point, because in general relativity, the gamma that you use is defined to be symmetric in the lower two indices. But let me stress that that is not a general definition. When we define parallel transport, we can do that by just introducing the connection, and the only demand on the connection, remember, is the following. It's made out of d cube components, which transforms under a change of coordinates like this. So the original gamma ABCs were not symmetric. Then despite this term being symmetric in j and k, the overall thing would not have been symmetric in j and k. It turns out that if you have a flat space-time where you can introduce Cartesian coordinates if you wanted to, this term is always 0. So this ensures that for such situations at least, and not uniquely to such situations however, gamma is symmetric in the lower two indices. Now with this out of the way, let us start calculating the gamma. Remember once again, our x1, x2 are nothing but x and y. X prime 1 and x prime 2 are r and theta. Well, I'm not very sure whether you can read this as prime. It looked more like x11 to me. So let's see whether I can remedy that. X prime 1 and x prime 2. Now, let's calculate the gammas in the polar coordinate system, where instead of I, j, k, I'm using r and theta as a value, by using our expression. That is, just using this term. Now, one more thing. when you are writing gammas with abstract indices I, j, k or ABC, you have really no way of knowing from that whether you are using the old coordinate gamma or the new coordinate gamma, which is why we have put a prime on the gamma here. However, in what follows, for polar coordinates, we are going to use r and theta and not numerical values for the indices. What that means is just by seeing whether the index has r's in it, I will be sure that you are talking about the polar coordinates. R's or thetas, that is. Well, you will not see things like gamma x, xy or things of that kind simply because we have already established that they are all 0. So what is gamma r, rr? Well, according to this formula, del r is sitting here, the new coordinate, and here also you have del r and del r, j and k are both same, and this has a del x say, del 2x say, that is a sum over the old coordinates x and y. So you have a del 2x, del x here, and del 2y with del y in this, and you add those two things together to get gamma r, rr. Now how much is it? Remember once again that we already know the transformation rule. X is r cos theta, y is r sin theta. Those are the inverse transformation rules. The direct ones, r and theta in terms of x and y, are basically, and theta is tan inverse y by x. Now del r del x, calculated from r equals square root of x square plus y square, simply x by root over x square plus y square. But what is important is x and y both are linear in r. R occurs in their expression only as a factor with power 1, which means if you differentiate that twice with respect to r, it's going to vanish. So whatever del r del x is, and you know what that is, I know that this term will contribute 0 because del 2x del r 2, that's what del r here means actually, is definitely 0. Similarly, the second term, del r del y is y over square root of x square plus y square, but del 2y del r2 is again 0. So, this particular connection coefficient, gamma r, rr, is 0. Now, let us systematically keep running down all the connection coefficients. Thankfully, you don't really have too many of them. You have only 8 because each index can take only 2 values, and among them also symmetry makes your life a bit easier. So let's now look at gamma r, r theta. We already know that it must be the same as gamma r, theta r. So just take these indices and place them first. So this r contributes to del r here, this r and theta contributes del r del theta here, and then you sum up over all the old coordinates x and y. So del x, del 2x, del y, del 2y, added together. Now del r del x, del r del y we have already calculated in the last step, so we just plug them in. What about del 2x, del r del theta? Well, if you differentiate del x with respect to r once, you simply get cosine theta. Differentiate that once again with respect to theta, gives you minus sine theta. Similarly, this one, del 2y del r del theta, gives you plus cos theta. But now notice, x by root over x square plus y square is nothing but cosine theta. And this is nothing but sine theta. So add the two terms together, you end up with 0. So these two connection coefficients also vanish. Well, the final one with r in the upstairs index is gamma r theta theta. And once again, you know the drill by now, del r, del theta in both of these terms, and del x, del 2x here, del y, del 2y here, added together. Now, we already know this derivative, so we write this down. This one is new, but that's pretty straightforward. You are differentiating cosine theta twice with respect to theta, which means you get minus cosine theta. And r, of course, stays intact. Similarly, this will be minus r sine theta. Remember, both cosine theta and sine theta return to negatives of themselves if you differentiate them twice. Now, in order to understand this better, let's convert everything to polar coordinates. X by over x square plus y square is simply cosine theta. So this term becomes minus r cos square theta. This one is sine theta, so this becomes minus r sine square theta. So this is our first non-zero connection coefficient. Gamma r theta theta turns into minus r. Let me stress once again that because the gammas are not tensorial, the fact that they all vanish in the Cartesian coordinate system for flat space does not mean that they are all going to vanish in some other coordinate system. In fact, in polar, some of the coefficients are still 0, but gamma r theta theta, this connection coefficient is not 0, it's minus r. Now quickly let us go over to the other 4 connection coefficients. These 4 had r as the upstairs index, the other 4 will have theta as the upstairs index. So gamma theta r, del theta del r, that is del 2r, del x, del 2x, del y, del 2y in both sums, and then you add them together. Now once again, x is linear in r. So del 2x del r2 vanishes, so does del 2y del r2. And therefore, you end up with 2 terms which have zeros in them. I have written down these derivatives because we will need them soon. But anyway, they are being multiplied by 0 here. So it wouldn't have hurt if we had just dropped everything here. The upshot is gamma theta rr is 0. Well, let's come to gamma theta r theta, which is same as gamma theta theta r. So del theta del x times del 2x del r del theta plus del theta del y del 2y del r del theta. And now let's put in the values. Del theta del x is minus y by x square plus y square. And the second derivative of x with respect to r and theta, this mixed derivative, well, it evaluates in the following manner. It's easiest to do the r derivative first, which will just give you cosine theta. Then you differentiate to get minus sine theta. Similarly, this is x over x square plus y square. And this derivative essentially is the derivative with respect to theta of sine theta, so just cos theta. Once again, let's put everything together. This is actually minus sine theta by r, and this is cosine theta by r. So what you end up with is 1 over r sine square theta plus 1 over r cosine square theta, which by the magic of trigonometry that we all know and love is simply 1 over r. Finally, gamma theta theta theta. Of course, by now you should be pretty familiar of this expression. But let me warn you once again, you will get this expression or expressions of this kind only because you are in a space, you are using a geometry in which the Cartesian coordinates exist, in which you have a coordinate system where all the gammas were to vanish. Anyway, by plugging in the values, which you already know how to calculate, and anyways they're pretty simple to, ends up giving you 0 once again. So ultimately what happens is we know that among all of these non-zero 8 possibilities, there are only 1, 2 and 3 non-zero terms. All other 5 components of gammas vanish even in polar coordinates. But now let us try to understand why the gammas are the way they are by invoking our standard notion of parallelity. Let me remind you once again that the geometry that we are using is standard Euclidean geometry. So irrespective of what the basis does when you go from one point to another, the vector being parallelly transported is parallelly transported according to the standard definition that we use in Euclidean geometry. Something which maintains a constant length and same constant direction throughout. Let us now try to use this and elementary geometry to figure out what the polar coordinate connection coefficients will be. Of course, we have already worked out the answer, but this time we are going to do this using geometry, and I'm pretty sure many of you will find this particular derivation pretty interesting and This will help you understand exactly what we mean when we say connection coefficients are connected to parallel transport. Let us now take a look at how that is done. Remember that in polar coordinates, though vectors do not change in length and direction during parallel transport, components do change. That's basically because basis vectors change from point to point. Now let me remind you about the basis vectors. If you are using polar coordinates, the basis vectors are things that we denote in differential geometry by del r and del theta respectively, and they are connected with our more familiar unit vectors that we use through the relationship that del r is er and del theta is r e theta. Before proceeding further, let me remind you once again about the formula which tells us how to introduce the gamma symbols via parallel transport. You start with any vector Vp at P and transport it parallelly to the point Q, giving me V parallel Q. If you take the ith components of this parallelly transported vector and subtract from it the ith component of the original vector, what I get is something which depends on the jth component of the vector, which is actually the vector P, and the kth component of the displacement. Of course, this term is really misleading because there is no specific component or the specific of the vector or a specific component of the displacement, which is actually important here. All components of the vector and all components of the displacement can potentially serve here. And coefficients which tell you how they combine together is minus gamma I kj. This may become a bit of a confusing thing later, so let me just stress this at this point, that the second index in the gamma is actually the index for the vector component, and the first index is the component of the displacement that we are actually using to go from the point P to the point Q. Of course, this will not be very confusing in most applications, because in most applications, gamma are going to be symmetric in the lower two indices. But in the more general case where they are not, it's important that the second index, the second lower index, is associated with the component of the vector, and the first lower index is associated with the component of the displacement. Now, let us put this equation into action, and for this we will start with a special vector at P. It has components of 1 and 0 respectively in polar coordinates. This is nothing but the vector del r at P, or in more familiar language, the unit vector in the radial direction. So let's focus on the picture on the left here. This is the point P with coordinates r theta. This is a neighboring point Q with coordinates r plus delta r and theta plus delta theta. Now we have started with our basis vector del r. That's simply because that will give us simple components to put in these equations. Now this del r or er hat, whatever you call it, this blue vector is the del r at the point P. If you parallel transport it to the neighboring point Q, you get this gray vector, which is VQ parallel. It's easy to see that this vector and this vector are of the same length and are in the same direction, which is exactly what parallel transport means when we are dealing with flat space. Notice that at the point P, the vector that we are talking about is already one of the basis vectors used. The other basis vector, the basis vector del theta, is of course perpendicular to Vp. By the way, this perpendicularity is a special feature of the polar coordinates or similar so-called orthogonal coordinates. This does not necessarily follow for a general coordinate transformation. Of course, here we already know that del r and del theta are basically in the same direction as er hat and e theta hat, which are known to be perpendicular. So, The perpendicularity is fine. Now what about the basis vectors at Q? Remember the very fact that in flat space-time you can have non-zero connection coefficients at all basically depend on the fact that the basis vectors change from point to point. So at Q, the basis vector del r there, or is basically the unit radial vector there, length 1, but it's in the radial direction. So starting from the origin, if you were to draw a straight line to Q and extend this further by unit length, you will get this blue vector, which is the del r at the point Q, and as you can clearly see, it's not the parallel transported version of this blue vector Vp. So del r at P, when you move it parallelly to the point Q, you get Vq parallel, which is not the same as the del r at the point Q. Of course, that means that this vector has non-zero components in both the del r direction and the del theta direction. So this is of course the other basis vector that you use at the point Q, del theta, and of course this is perpendicular to this blue vector as you expect. But one important thing is, while these two blue vectors, the del r's at the 2 points, both have the same length, the del theta vectors do not. So there's a change in direction, of course, that's there in the del r as well. But remember that length of this vector is essentially r, whereas the length of this vector is r plus delta r. Now, to calculate exactly how much the change in the components of VQ are, let's take a look at this blown up version of the same picture. This is taken at the point Q. You just take this region, blow it up. So this is the del r vector at the point Q. This is the del theta vector at the point Q. The length of the del theta vector at the point Q is r plus delta r. The length of the vector del r is simply 1. And along with the basis vectors, I have also drawn the most important thing here, which is VQ parallel. So this gray vector here, this one is VQ parallel. Now, geometrically, what we can immediately say about VQ parallel is the following. Its length has to be the same as VP. So it has length 1. And the angle here, this angle, is actually the same, as you can easily check from elementary geometry, as this angle, the angle between the two radial vectors joining the origin to the points P and Q. Of course, this angle is nothing but the change in the polar coordinate theta, delta theta. So this is the delta theta angle between them. Armed with this information, it's actually very, very easy to find out the two components from elementary vector algebra. This vector of unit length has a radial component, cosine of delta theta, cosine of this angle, and the cross radial component whose length is minus sine delta theta. Minus because of course it's directed opposite to the del theta component. But remember, the length being minus sine delta theta, of course the minus is just the directions, length is sine delta theta. That does not tell you that the component is minus sine delta theta. Note that the basis vector itself has a length of r plus delta r. So the component is minus sine delta theta divided by r plus delta r. So when you form the VQ parallel vector by coupling both the components and the basis vectors, the length of the basis vector cancels with this r plus delta r, giving us the geometrically correct result. But the important thing to realize is we are really interested in this rather complicated looking expression only in the limit when delta theta and delta r are very tiny. So only first order in delta theta. Now cosine delta theta is almost 1. In fact, to first order in delta theta, it is 1. It deviates from 1 only in the second order. Minus sine delta theta, that's easy. We know that it can be replaced by delta theta. The r plus delta r can be written down as 1 plus delta r over r inverse with a 1 over r outside. and that when expanded would give you 1 minus delta r by r plus square of that minus square cube of that and so on. But since there's already a delta theta outside, any term with delta r by r in it or higher powers in it would be higher than linear power in the small quantities. So we just ignored them. So to first order, this expression simply becomes 1 comma minus delta theta by r. This, remember, is VQ parallel. So what is the difference between VQ parallel and VP? Here, of course, I have written both components together. There is a del r component or r component. There is a theta component. And remember, VP had components of 1 and 0. So difference is simply 0 comma minus delta theta by r. Now, let us rewrite this in terms of connection coefficients according to the expression that we have. Going back once again, the ith component of VQ parallel minus VP is going to be minus gamma I upstairs Kj Vj delta xk. Vj is associated with the second index of gamma. Now here our Vj has components of 1 and 0, only a radial component, which means the only non-zero terms we will have r here. K can take both r and theta as values because delta x has both delta xr and delta theta. Has both delta r and delta theta. So now, in terms of that expression, you have r upstairs in all the terms. So this is for the two components. There is a r component, there is a theta component. This one has r upstairs, this one has theta upstairs. The second index here is forced to be r because our VP had only one non-zero component which was equal to 1. And now, here also for the theta component as well, the second index below is always r, forced by VP being 1, 0. But then the summation is over the first index, that's the residual summation, r delta r, gamma r theta r delta theta. Similarly here you have minus gamma theta r delta r minus gamma theta theta r delta theta. Now we already know what that is. It's 0 for the first component minus delta theta over r for the second component. And from this we can immediately see that these two coefficients have to be 0. Remember, delta r and delta theta are independent quantities. You can make one 0 without making the other 0 and so on. And that tells you that both coefficients must vanish for this expression to be 0. On the other hand, for the theta component, you can immediately see that the coefficient of delta theta is not 0. That the coefficient of delta theta has to be 1 over r. So that gamma theta theta r is 1 over r. That's something you derive or work out from the basic definition and the basic geometry of the way in which the del r vector gets parallel transported from P to Q. To finish our calculation or this new kind of derivation, we need to look at another vector, del theta in this case. The vector P is simply del theta. It has components 0 and 1. And what that of course means is that at P is this vector. You parallel transport it here, exactly same length and same direction as this one. And now, in terms of the basis vectors at the point Q, the expression for VQ parallel has to be figured out. Once again, let's blow this up here and look at this, the larger scale. Note that the length of the vector del r is 1. The length of the vector del theta at the point Q is r plus delta r, not 1. Whereas the length of this parallel transported vector VQ parallel is actually r because it has the same length as the vector at P, where of course the cross radial vector del theta has a length of r. So now, armed with this knowledge and also the simple geometrical fact that this angle has to be the angle between these two radial vectors, of course These are perpendicular. The green one here, Vp, and the green one at Q are perpendicular to the respective radial vectors, and this Vp has the same direction as VQ parallel, which is VQ parallel, and this delta theta at Q have an angle of delta theta between them. Next comes figuring out the components. Well, the radial component is simply this length, which is r, the length of this vector, times sine of delta theta. What about the theta component? The theta component is slightly trickier. Would have been r cos delta theta if you were to just go by the magnitude, but since the basis vector has a length of r plus delta r, the component is r over r plus delta r cosine delta theta. Now we come to small delta theta and delta r. The first term is trivial, it's r delta theta, something we have learned from the very first time that we had learned about calculus, if not even earlier. What about this? Cosine delta theta is 1 to first order. Any changes is in the second order. And r by r plus delta r is essentially 1 plus delta r by r to the power minus 1, which expands to 1 minus delta r by r plus higher order terms. If we are keeping only up to first order, this is where the thing ends. So this is VQ parallel. Vp, of course, was 0, 1. Subtracting that from VQ parallel gives you r delta theta and minus delta r by r as the two non-zero components, but there are only two components, both of them are non-zero, of this change in the vector because of parallel transport. Well, once again, let me remind you that this second index in all of these terms have to be theta, because only del del theta has a non-zero coefficient, which is 1 for our vector. The upstairs index has to be whichever component you're talking about, r for the first two terms, theta for the second two terms, which belong to the second component. The first index talks about the displacement. So you have r here and delta r, theta here and delta theta, and so on. Now, from the fact that this expression is r delta theta, it's easy to see that minus gamma r theta theta has to be r. So gamma r theta theta has to be minus r. And from this expression being minus delta r by r, it follows that gamma theta r theta is 1 over r. So in flat 2D space described by polar coordinates, the only non-zero connection coefficients would be gamma r theta theta, gamma r theta, and gamma r theta r. And you should check for yourselves, if you have not done that already, that these values that we have obtained here are exactly the same as the ones we obtained analytically by using the transformational law for connection coefficients. This should hopefully give you a better understanding of exactly what the connection coefficients mean geometrically. By the way, in this derivation, we saw that if you start with Cartesian coordinates in flat space and then go over to some other coordinate system, the corresponding gamma must be symmetric in the lower two indices. Now this actually happens to be a property of a very important class of connections. Technically, these are called torsion-free connections. The kind of geometry that we use in general relativity, for example, is called Riemannian geometry, and there this gamma, the connection has another important restriction. We will see in the next class that the restriction happens to be metric compatibility, something which essentially says that the covariant derivative of a metric tensor must be 0. Now, many of you already know what a metric tensor is. Those who do not, don't worry. We are going to talk about that in detail in the next lecture, and also establish explicit formulas for the gamma ijk's in terms of the metric tensor. But that will of course have to wait for another day. Bye for now.